Yet another first-hop redundancy protocol is Gateway Load Balancing Protocol, or GLBP. And as the name suggests, in addition to being a first-hop redundancy protocol, which it is, it can give us some load balancing. Remember, with HSRP, we might have a couple of routers that could get us off of our local subnet. Same thing with VRRP, but one of those routers was active, or it was the master router with VRRP for a particular group. And that one router was servicing a virtual IP address and the corresponding virtual MAC address. Well, with Gateway Load Balancing Protocol, we could have, for example, 4 different routers, each of which could get us off of a local subnet. And instead of having one be active and the others just waiting for that active router to fail, we could load balance across all of those routers. In this topology on screen, I've got a couple of routers, and let's take a look at how we could load balance traffic going off of the network. The way that GLBP does its magic is it has something called an AVG, an Active Virtual Gateway. And the Active Virtual Gateway is in charge of handing out MAC addresses in response to ARP queries. And these MAC addresses are going to be the MAC addresses of AVFs. An AVF is an Active Virtual Forwarder. It's a router that's able to get traffic off of a local network. And in this topology on screen, router R1 is the AVG, but it's also an AVF. It could also get traffic off of the local network, and we'll say that it has a MAC address of all ones. And R2, that's another way of getting off of this local network. It's an AVF, it's an active virtual forwarder, and it has a MAC address of all twos. And we'll say that the virtual IP address being serviced by this GLBP group is 10.1.1.1. And what's going to happen when these PCs send an ARP request saying, what is the MAC address corresponding to my default gateway's IP address of 10.1.1.1? What's going to happen is the AVG, the Active Virtual Gateway, R1, it's going to respond differently to the same question. For example, PC1 is going to send out an ARP request saying, hey, can somebody tell me the MAC address corresponding to 10.1.1.1? That's the responsibility of the AVG to respond to that, and it's going to respond to that question and say, oh, the MAC address for 10.1.1.1 is the all ones MAC address. In other words, PC1 is going to be pointing to the MAC address of R1 when it's sending traffic to 10.1.1.1. Now, PC2 is going to send out an ARP broadcast asking the very same question. PC2 says, hey, can somebody tell me the MAC address for 10.1.1.1? And this time, the AVG responds differently. This time it says, sure, the MAC address for 10.1.1.1 is the all twos MAC address, which is the MAC address associated with router R2. That's how the load balancing happens. The AVG can give out different MAC addresses in response to ARP queries, all of which are saying, hey, what's the MAC address for this default gateway IP address? And we can get fairly advanced with our configuration. We could associate different weights with different active virtual forwarders, where maybe one AVF is getting 75% of the traffic, and another AVF is getting only 25% of the traffic. We could influence the load balancing, in other words, with weightings. And remember, we talked about tracking with HSRP and VRRP. We have tracking available with GLBP as well, and with GLBP, if we're tracking an interface or we're tracking an object, what we can do is decrement not the priority of a GLBP group, we can decrement the weight of a specific AVF. For example, let's say that R2 had a metric to get to a particular route out on the internet or out on the corporate network, and that metric was 1 million. We could say that if that metric ever worsened, if it ever got worse than 1.5 million, for example, we could say that's going to trigger this tracking object to go down. And if that tracking object went down, then we could decrement the weight of R2. It would receive less traffic as a result. And we could say if the weight gets too low, then the AVG is no longer going to hand out the MAC address of an AVF. Now, from a troubleshooting perspective, what sorts of things are we looking for? Similar to what we were looking for with HSRP and VRRP, let's identify the different roles. Who is the AVG? Who's the active virtual gateway that's going to be handing out MAC addresses in response to ARP queries? What is the virtual IP address that we're servicing with this GLBP group? What are the virtual MAC addresses of the AVFs that we have? And maybe we think one router should be the AVG, but it's another router. Well, we might want to check things like priority and preemption, like we did with HSRP and VRRP. And also, we might want to check to see if we're referencing any tracking objects, which might influence the weight, which could influence load balancing and maybe even take an AVF out of rotation if that weight got too low. Let's go out to a live interface right now and see how we could gather some of this GLBP information. Let's begin by taking a look at PC1 and PC2. I'm going to do a ping to an internet address of 1.1.1.1. And in order to get there, I had to go through my default gateway, which means that PC1 had to do an ARP saying, hey, can somebody tell me the MAC address for an IP address of 10.1.1.1? We should now have that MAC address in our ARP cache. Let's do a show ARP. And for 10.1.1.1, this is the MAC address. Notice it ends in 0A01. Let's do the same thing on PC2. On PC2, let's do a ping to 1.1.1.1. And let's do a show ARP here as well. Notice that PC2 has the same default gateway as PC1. It's still 10.1.1.1, but the MAC address is different. The last 4 hexadecimal digits on PC1 were 0A01. Here on PC2, it's 0A02. Different MAC addresses. This is how our load balancing works. Now let's go to routers R1 and R2 and gather some GLBP information. Let's see, who is the AVG? What are the MAC addresses being serviced by the different AVFs? And much like we could do a show standby brief command with HSRP or show VRRP brief with VRRP, I can do a show GLBP brief command to get a nice overview of what's happening. The top line in the output is indicating the active virtual gateway that's responsible for handing out the MAC addresses. And we can see that the active router is us. It's local. The standby router is 10.1.1.3. R2, in other words, is capable of handing out MAC addresses, but right now it's us. And then we can see for our different forwarders, we have 2 of them, we can see what are their MAC addresses. It looks like R1, the local router, is the active router for this MAC address. This was the MAC address to which PC1 was pointing, if you remember. And we're in the listen state. In other words, we're standing by to service this MAC address, but right now it's not us. Right now, the router that's actively servicing that MAC address, which by the way was being used by PC2, that router is 10.1.1.3. That's R2. We can get more detailed information by saying show GLBP, and we could follow that with the interface identifier, Fast Ethernet 0/0 in our case. And we can see that for the AVG, our state is active. Here's the virtual IP address that we are servicing. Notice the hello and hold times are the same as they were by default with HSRP, and like HSRP, GLBP is a Cisco proprietary protocol. We see that preemption is enabled. It's not by default, but I enabled preemption on these routers. We see that we are active and the standby is R2. R2 has a priority of 100. We have a priority of 110. And we can see the members of this GLBP group. We've got R1, which is us, and we've got R2. Oh, and by the way, you can do authentication with our first hop redundancy protocols. And if you do, those authentication credentials need to match. I'm configured for MD5 authentication using a key string, and those key strings are matching. And let's take a look at our different forwarders. Here's forwarder 1 and forwarder 2. We can see the MAC address associated with each of those forwarders, and we can see the weighting associated with each of those forwarders. I just took the default. We could go in and manually configure weighting to hand out the MAC address of a particular AVF a higher percentage of the time if we wanted to do that. And if we were tracking an interface state, or if we were tracking an object, we could say that we want to decrement one of these weightings if that object went down. And we could set a threshold to say if the weighting ever drops below a certain value, then the AVG is going to stop handing out that AVF's MAC address in response to ARP queries. If we want to do some debugging, we could do the debug GLBP terse command like we could with HSRP. VRRP, by the way, did not have a terse option. You would have to give multiple debug commands to get all of that information. But here I'll do a debug GLBP terse command, and let's go to router R2 and let's shut down interface Fast Ethernet 0/0. Let's go into interface Fast Ethernet 0/0. Let's do a shutdown and see what happens over on R1. We're going to notice that that interface is down. We're going to stop receiving hello messages, and it means that R1 is going to transition to an active state for forwarder 2. It's going to start servicing forwarder 2's MAC address. We can see here in the output of the debug command that we're transitioning from listen to active. Let's do a U all to turn off all of our debugging, and once again do a show GLBP brief command. And we can see that we are now active for both forwarders. We are now servicing both of these MAC addresses, meaning that when PC1 wants to get off of its local subnet out to the internet, it's going to go through R1 right now, and so is PC2. I'll go back to R2 and we'll bring this back up. I'll do a no shutdown. And after we do that, R2 is going to transition back to the active AVF for forwarder 2. Now if I do a show GLBP brief command, looks like our timer has not expired yet because R1 is still active. However, it looks like we just went from active to listen, so let's issue that command once again. And now we see we're back in the listen state. R2 is now once again servicing this MAC address. And that's a look at GLBP, a Cisco proprietary first hop redundancy protocol, which in addition to giving us redundancy, gives us load balancing.